Okay, now we're going to do a couple of examples of goodness of fit test. This is again Intro to Stats. The speaker is Mark Lesperance. The first example we're going to do is suppose that we have a staff member at Emergency Medical Service, which is determined whether the number of accidents is equally distributed during the week. A week was selected at random and the following data were obtained. We're going to test the hypothesis that the number of accidents is equally distributed throughout the week at an alpha equals 0.05 level. And we have the following number of accidents were observed on each day. So let's go to working with calculating our test statistic. The first thing that we need to do is add up and see what the total is of observations. And in this case, the total observations, there's 189. If we assume that the day, or that each day is equally likely to have the same number of accidents, then we should have an expected count that's equal on every one of these days. So that means 1/7 of the total should occur on each day. And if I look at 189 over 7, that's equal to 27. So that gives me an expected count of 27 on each day. Should still add up to be 189. The only difference is for our expected, we assumed that they were the same number on every day. So now the next step in calculating our test statistic is to look at the observed minus the expected squared over the expected. So in this case, it would be 28 minus 27 squared over 27. And 32 minus 27 squared over 27. And 15 minus 27 squared over 27. We take the observed column minus the expected column. We square each of those answers, and we divide by the expected number in that column. And we could continue doing this all the way down, and then we will add all of those up. So again, these are the values that we're getting. We're taking the observed minus the expected quantity squared over E. Now, if we simplify that, see if I can write it so that it's readable. For each one of these, the first one's going to be 0.037, and then 0.926, and 5.333, and 6.259, and 4.481, and 9.481, and 2.370. If I add all those up, I get 28.889. This value is our test statistic. Okay, right? This was a chi-squared value. They do it as chi-squared sub 0, or we want chi-squared sub test, is the sum of the observed minus the expected squared over the expected. So we did each one of these items here, and then we added up that column, which gave us the sum. So note that if we want a critical value, let's see, there were 7 days of the week here. So that means there are 7 categories. There are then 6 degrees of freedom. So we're going to go to the chi-squared table. We're going to look in the 6th row for 6 degrees of freedom, and the 0.05 column, because that was the alpha that we had, and we end up with our critical value of 12.59, and since 28.889 is greater than 12.59, we reject. And we would conclude that the days are not equally likely to occur. Again, we looked up our critical value of 12.59. Our test statistic exceeded that value, so we will reject the null hypothesis. We will conclude that days are not equally likely to occur, to have the same number of accidents. If we wanted to try to figure out the p-value, notice that 28 is further out than this 20.52. We would have a p-value less than 0.001. If we wanted to do this in StatCrunch, we could come up here and we could put in day and observation. And this would be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. We have 28, 32, 15, 14, 38, 43, and 19. So we enter that information into StatCrunch. I can go to Stat, Goodness of Fit, chi-squared. My observed column is observed. Now, I can either make an expected column and add that in here, or, as this one is doing, it says all cells are in equal proportion. So that means that each category is equally likely to occur. If I hit compute, notice it shows me the expected value of 27 on each one. That was corresponding to the fact that we knew it was equally likely to occur. It shows us the chi-squared statistic that we calculated. It also shows us that we had a p-value less than 0.0001. So it was even further out on the table than what we thought. So the second example is, suppose that in a previous election for president, that 50% of registered voters were Republicans, 40% were Democrat, and 10% were independent. Prior to the upcoming election, a random sample of 200 voters showed that 90 were Republican, 80 were Democrat, and 30 were independent. We want to know, is there sufficient evidence to conclude that the distribution of voters has changed or is different than the previous election years? We want to conduct a test at alpha equals 0.01. So this is a little bit different problem, but similar in nature. What I mean by different but similar is that we're still working with a perspective of what the percentages of each category should be. Before, we were talking about equally likely, so that meant that 1/7 of the observation should happen on each day. Here we have some preconceived idea of what the percentages for each category should be. We can use those percentages to help us come up with the expected number of observations. So, if I had 200 total observations, I would expect that 100 would be Republican, 80 would be Democrat, and 20 would be independent. Still going to add to 200, but I'm going to apply these percentages to that 200. 50% of 200 is 100, 40% of 200 is 80, 10% of 200 is 20. Now we're going to go through the same process, and we're going to look at expected value minus observed squared over E. And I actually have enough room on this example that I can show the calculations and the final result. So this is going to be 90 minus 10, or minus 100, squared over 100, which is going to be 1. 90 minus 100 is minus 10, squared is 100, divided by 100 is 1. 80 minus 80 over squared over 100 is 0. And 30 minus 20 squared, oops, this would be over 80, not 100, over 20 is equal to 5. So total, we get 6. Again, that's our test statistic. So our test statistic is 6. The critical value is the chi-squared value looking in the 0.01 column with 2 degrees of freedom. Where does the 2 come from? There were 3 categories, so I get n minus 1 degrees of freedom, which is 2. So I'm going to go to my chi-squared table. I'm going to look in the 2 row and the 0.01 column. I see 9.21. So this is 9.21. Because my test statistic is less than my critical value, we fail to reject. We do not have enough evidence to say that the distribution has changed. If we want a p-value, we would again go back to the 2 row. We would look to see where we saw 6, and notice it's just a little above 0.05, but it's between 0.05 and 0.025. So we would have p is less than 0.05 and greater than 0.025. So at a 1% level, we failed to reject the null hypothesis. If we had chosen a 5% level, we would have had a marginal case where we rejected. And the p-value is actually probably somewhere around 0.0501, but let's calculate it. Let's go over to StatCrunch. And we will go in and we will put in party and observed. And here we will need to do an expected column because they're not equally likely to happen. So we had, whoops. Go back to my example here. I do have one mistake. I wrote down the numbers in the order in which they were given, but I did not write down the parties in the order in which they were given. So this is Republican, Democrat, Independent. So that's still, the calculations are correct. The conclusion we drew was correct. It's just I didn't have them in the correct order on the name side of it. All of the values we had were correct. Okay, so let's go back and do our StatCrunch. So we're going to do Republican, Democrat, Independent, expected or observed is 90, 80, 30, and expected is 100, 80, 20. We'll go to stat, goodness of fit, chi-squared. Our observed column is in little OBS. The expected is in the expected column, and I can compute. And notice that I end up with this chi-squared test statistic value of 6 and a p-value of 0.04098. So we were just under the 0.05. So it's greater than 0.01, which was our level of significance. Because this is greater than 0.01, we would fail to reject. Again, remember that whether or not you accept or you reject or fail to reject will depend on the level of alpha that you set. If I had set a 5% level of alpha, we would have rejected the null hypothesis. Since we were given a 1% level, we would fail to reject. So this concludes our discussion of examples of goodness of fit.